It means simply that the process, which might look like this, I know it's discrete time, but all right, sample it. That the probability distribution on what happens here is the same as the probability distribution on what happens here, k translated, with a translative k. And that's for all k and all sized windows. So, notice we are not demanding that the xi's be IID. If the xi's are independent and identically distributed, then the process is stationary. But you can have all sorts of dependence, including dependence on the infinite past, and still have a stationary process. Stationarity means really two things for us. One is you can't tell time. Like if you look here, you can't tell, oh, the time is if the time here is 0, you can't tell that the time here isn't 0 just by looking at that. So you can't tell time. Really what it means is the stochastic process is in equilibrium. Every batch looks like every other batch in distribution. So it's in physics that would be equilibrium. Here. So you can't tell time by this. For example, or if this is the ocean, let's look, we're out 1,000 miles off the coast of Hawaii and the ocean looks like that. You take a snapshot and then you go 3,000 miles off Hawaii and take another snapshot. The distribution of this and the distribution of that will be the same if the ocean is a stationary stochastic process, indexed by space, xy. Here's a challenge for you. I said you can't tell time here, but maybe you can tell the direction of time for a stationary process. Send me an email if you can define for me a stationary process in which the direction of time is a necessary, conclusion from your inspection of it. Now, I don't mean just you give me this process. Yeah, it looks different this way than it looks that way. But which way is time? Time going forward. Well, you can't. Yes, there's an asymmetry, but no, there isn't one that reveals the direction of time. You say, all right, interesting. But that's exactly what we're doing. Is it now 5 seconds later than it was when I started the sentence? Well, yeah, you'd all say so. There's a coffee cup break, et cetera, et cetera. You see a movie, is it going forwards or backwards? You know that. So we can tell the direction, the arrow of time, from the sequence of snapshots we have of the stochastic process we call our universe. So how can we do that? I'm going to claim you're not going to be able to send me the email. Yes. How would you define forward in time? I mean, I don't want to put you on the spot.
Sure, I guess.
I mean, don't you feel that the future is different from?
Sure, but
Yeah.
we redefine what forward means.
Oh well,
The universe where forward moves backwards and backwards moves forward.
yeah, you can change the words, but that doesn't mean that you can change the feeling. I mean, like I can remember the past, but I can't change it. I can change the future, but I can't remember it. There seems to be an asymmetry. So, what we're observing are snapshots, say from a finite alphabet, because the resolution of our experiments of what the current state of the world is, probably is, there's a finite number of resolvable states that we can measure, that is, distinguishable states. And so, apparently from these snapshots, we can tell the arrow of time. Yes? The direction at which entropy? Entropy increases. Not really. Yes and no. Yes and no. Remember, there's something weird going on, and we'll get into that on Tuesday, that even with symmetric physical laws, you can have the notion of entropy increasing in one direction. So how is that? How do you get an asymmetric consequence, something as fundamental as the second law of thermal, out of nothing but time symmetry? All right, good. All right, let's do some more definitions here. We have Markov, which we've talked about a lot, xi, in which the probability of the next term given the past is just p of xn plus 1, given the most recent past as indexed. Here, past is what I say it is. It's the index. A Markov process with a finite state space is defined by Pij, j. When I'm in state I go to state j with probability p sub ij. So we have a matrix. Let's suppose the alphabet's of size m, and the matrix then is P1, P2, which is the entries of which are Pij. And it's m by m. And the every row sum, summation Pij, summed over j, the columns, where we're going, is equal to 1. So I've got to go somewhere. And so this gives me a probability transition matrix for a Markov chain. And if this doesn't change within, we call it a time invariant Markov chain. So P. So just giving this will define it. As long as you define the initial state, then the stochastic process is totally well defined. Now, not all Markov chains would be stationary, so let's make it stationary. So we have definition of stationary distribution mu, and that has components mu1 through mu_m, where m is the number of states in the chain. And we demand that mu solves mu equals mu p. Is that right? Mu transpose p. Look, I'm not going to get into the transpose business. Mu equals mu p, which is mu j is summation of mu I, pij, summed over I. And that just simply says, if you have a Markov chain, and you look at state j, and you want to know the probability of state j, mu j, it's where the process was before mu I, pij, is the probability of transiting from I to j. So we sum over all the states it could have been before, times the probability we transit to state j, and we get the probability distribution on the states at the next unit of time. Now it's stationary if that probability distribution is the same after the one step of the Markov transition as it was before. If the distribution keeps changing, it's not in equilibrium, it's not stationary, you can tell time from the process. So this is what we mean by a stationary distribution. And here are some examples. Here are two states, 1 and 2. Here I'm going to go alpha, alpha bar, and I'm going to return from 2 to 1 with probability beta, beta bar. So a typical output would be 1, 2, 2, 2, 1, 2, 2, 1, etc. Now, how do we make this a stationary process? Well, we want the probability after one distribution on the states after one transition to be the same as it was before. But look at the flow of probability here. If this is mu1, then the flow of probability is mu1 alpha. And if this is mu2,